Okay, so you've seen numbers like pi, which is approximately equal to 3.1415 and so on. You've seen numbers like I, which is it is equal to the square root of -1. I want to show you a new number that's kind of like these two. It's called e, and it's named after a famous mathematician named Leonhard Euler. He spelled his name a little in a strange way, but he was a brilliant mathematician nonetheless. So he basically would have invented math if he had been around back then. And he discovered this constant called e, and he named it after his own last name, and e is approximately equal to 2.718281828, and then you think it's going to keep repeating 1828, 1828, 1828, 1828, but it's not. After this, it goes 45, 9, 0, 4, 5, and then it just keeps going. And it's an irrational number, just like pi, but it's a totally different constant. It's discovered by Leonhard Euler, and it has some really amazing and really crazy properties. So I want to show you some of those properties. Alright, so let's look at this expression right here. 1 plus 1 over n, all raised to the n power. Alright, so if n is, for example, 1, we'd have 1 plus 1 over 1, which is 2, raised to the 1 power, which is 2. Alright, if n is 2, we'd have 1.5 squared, which is 2.25. If n is 3, we have 1 plus a third, raised to the third power, which comes out to about 2.37. Now, here's a question mathematicians have asked, and the question is, what happens if n gets bigger and bigger and bigger? So, essentially, it approaches infinity. Well, here's what would happen. In this denominator, as n gets bigger and bigger, this whole fraction gets closer and closer to 0, right? It gets smaller and smaller. So, suppose n is 10 billion. We'd have 1 over 10 billion, a really small number. But then up here, we're raising 1 plus this really small number to a really big power. Because as n approaches infinity up here, any number other than 1, even if it's just slightly bigger than 1, raised to a really big power, is going to be really, really big. But then if we take 1, we can raise it to any power, and it's going to be 1. So this n wants to say, as I get bigger and bigger, 1 plus 1 over n raised to any power is going to get closer and closer to 1. This n says, as I get bigger and bigger, raise anything that's even just slightly greater than 1 to this power, and you're going to get a really big number. So this n wants you to get a 1 as your result. This n wants you to get a really, really big number as your result. And as n approaches infinity, these two n's, one in the denominator and one in the exponent, are just fighting it out. They're having this epic battle. What results you get? You end up getting e. As n approaches infinity, this approaches e. So that's one of the cool properties of e, is that the limit, here's the official mathematical way to write this, the limit as n approaches infinity of 1 plus 1 over n to the n is equal to e. Alright, so that's one of the cool things about e. Let's look at some more. Okay, here's the graph of an exponential function. Function of x equals e to the x. So if x is 0, e to the 0 is 1. If x is 1, 1 is about here. E to the 1 power is 2.718281828 roughly, so about here, right? So we've got the point 0, 1, the point, I don't know if you can see this or not, my pen there, 0, 1, let me make that a little darker, the point 1, e, and then 2 is about up here, and we get, if x is 2, then the function of x would be e squared, so 2e squared. And if you take 2.718281828 roughly and square it, you'll get just a little over 7. So this is the graph of function of x equals e to the x. So what's the big deal about this graph? Well, this graph has a really cool property. And in order to tell you about this property, I have to talk a little bit about calculus. So you already know that if a graph is a straight line, it has one slope throughout the whole graph. If we pretend this graph is the graph of the linear equation, for example, you can see how its graph has just one slope. But then we've got graphs like this one that curve. Well, how do you talk about slope of this graph? It actually has a different slope at each point on the curve. So right here, its slope looks something like this. But at a higher point on the graph, its slope will be a bit steeper, like this. At a point down here, its slope would be pretty shallow. And its slope is going to be what we call the line that is tangent to the graph. So it just barely touches the graph, doesn't touch the graph at more than one place. And it's the slope of that line. Alright, so that's all I'm going to tell you about calculus. But what I'm going to tell you about this graph is, for this graph of function of x equals e to the x, how can you figure out what the slope of this graph is at any point? It turns out that with this graph, at any given point, the slope of a line tangent to it is equal to the value of the graph at that point. So right here, let's take the point 0, 1, okay? The slope of the line tangent to it is about like this. What kind of slope does this look like to you? It's a slope of 1. So we're at the point where the function of x is equal to 1, and our slope is 1. Let's try this point right here. Well, that's a bad example. Let me try the point right here where the function of x is equal to 2. All right? Our slope is going to look about like that, and as you can sort of tell, not exactly, but just trust me on this, the slope is equal to 2. Up here, where suppose we let function of x equal 4. So find this point about right here. X is going to be almost 2, not quite, maybe 3/4 or something like that. And the slope is going to be 4. So whatever the function of x is, that's going to be the same value as the slope. This is the only graph for which that is true. So that's a really cool property of E. Okay, here's another graph. This graph is the function of x equals 1 over x, or y equals 1 over x. So if x is 1, y is 1. If x is 2, y is a half. If x is 3, y is a third. If x is 4, y is a quarter, and so on. So this graph has a lot of interesting properties, but one of them involves the area under the graph. Differential calculus deals with the slope, or the rate of change, at a certain point on the graph. Well, there's another kind of calculus called integral calculus that deals with the area under a curve. So suppose I want to take from this point, from the point 1, 1, where x is 1 and y equals 1, and I want to find the area under this curve up to a given point. How am I going to calculate the area under the curve? Well, since it's curved, you can't use geometry the way that you normally would. You're going to have to use calculus. So if I'm going to shade the area under this curve from, say, 1 to 2, as you can tell, it's not quite the area of 1, because a square here would be an area of 1, and as you can see, this is slightly less than what a square would be. So how far do I have to go to get an area of 1? Well, let me just keep going for a while. And it turns out that right at this point, about, is where I would get an area of 1. And what do you think the x-coordinate of this point is? E. And then the y-coordinate, of course, is 1 over e. So the area from 1 to e, the area under this graph, is exactly 1. Alright, let me show you one more graph. So this is a graph of a pretty interesting function. Y equals not the square root of x, not the cube root of x, not the fourth root of x, but the x root of x. So that's where it gets this funky shape. It starts out pretty small, gets up, gets to a highest point, and then if you keep on going and going and going, it's going to be going down. And it's going to be getting closer and closer to a value of 1. So as x approaches infinity, y approaches 1. But what is this highest point before it starts going back down? The highest point turns out to be when x equals e. So the e root of e is the highest point on this graph. Okay, so why do I have a die, a coin, and then a drawing of a basketball up here? Well, they all have one thing in common: probability. If you roll a die, there's a 1 in 6 chance that you will get a 6, or any other number for that matter. If you flip a coin, there's a 1 in 2, or a 50-50 chance that you'll get heads. And have you ever heard somebody use the term, that shot was 1 in a million? Well, they may be exaggerating a little bit, but let's suppose there actually were a shot that is 1 in a million. Well, here's a question that I want to ask you. If you shoot that shot 1,000,000 times, are you guaranteed to hit one of them? Well, here's a coin. If you flip it, there's a 1 in 2 chance that you'll get heads. If you flip it twice, are you guaranteed to get heads? The answer is no. If you roll this die 6 times, are you guaranteed to get at least 1 6? Again, the answer is no. So we can assume then that if you shoot a 1 in a million shot 1,000,000 times, that doesn't necessarily guarantee you that you will score a basket. For me, it certainly doesn't. But then, what is the probability that you will score if you shoot 1,000,000 times? Well, in order to calculate a probability like that, you have to calculate actually the probability that it won't happen. For example, if you have a 50-50 chance of getting heads, and you want to calculate the probability that you will get heads if at least once or more, if you flip the coin twice, what you have to do is calculate the probability that you won't get heads, and then multiply it by itself each time you flip the coin. So to calculate the probability that you'll get heads at least once if you flip the coin twice, you would take the probability that you'll get tails, which is 50-50, multiply that by 50-50 because you're going to flip it twice, and then you would get 1 in 4. So there's a 1 in 4 chance that you won't get heads either time, which means that there's a 3 in 4 chance that you'll get heads at least one of those times. Now that's not the most important thing here, but what I'm trying to get across is that in order to calculate the probability that you will score a basket if you shoot 1,000,000 times, you have to calculate the probability that you won't score at all. Well, it turns out that the bigger the number gets, so if it's a 1 in a million chance and you shoot 1,000,000 times, or if it's a 1 in a billion chance and you shoot 1,000,000,000 times, or if it's a 1 in a trillion chance you shoot 1,000,000,000,000 times, the bigger that number gets, the closer the odds against you scoring at all get to, watch it, 1 over E. That's the odds. So if there's a 1 in infinity chance of you scoring, and you take the shot an infinite number of times, chances are 1 over E that you won't score at all. And then 1 over E turns out to be about 0.36 something or other. And if you subtract that, you get 0.63 something or other. And those are the odds that you actually will score. So if you have a 1 in a million chance and you shoot 1,000,000 times, you're not guaranteed to score, but you've still got a pretty good chance. You've got about a 0.63 something or other chance of scoring. So E has a pretty cool application in probability there, which is really interesting to think about. So I want to show you one more cool property. Alright, you remember the number I is the square root of -1. You remember pi is from geometry. It's the ratio of the diameter over the radius. And then we have our kind of go-to fallback numbers like 1, which is the kind of fallback number for multiplication, right? You multiply anything by 1, you're going to get the same thing. Then we have 0, which is kind of the fallback number for addition. And then we have this number E, this new number that has all these cool properties. Well, is there anything we can do that can relate all of these numbers in one equation? Mathematicians have discovered this equation that a lot of them consider to be the most beautiful equation in all of mathematics because it relates all of these numbers in just one equation. And let me show you that equation. To start with E, so you've got the number E raised to the pi times I power. So you're actually raising E to an imaginary power. Add 1, and you get 0. So E to the pi I is -1, it turns out, and then you add 1 and get 0. So you've got this one equation right here that relates the 5 most important constants in all of mathematics. E, pi, I, 1, and 0. All in one equation. And explaining how this equation works and how they prove this takes a long time. But I just wanted to show you that equation because it's a really cool equation that uses the number E. So those are some of the really cool properties of the number E, and that's why E should be one of your favorite numbers. Thanks.